So on Tuesday, the last two lectures, we introduced the course, what we are going to do with the course, and then we started some probability review from the fundamentals. We talked about some set theory fundamentals, we talked about the probability axioms, some associated corollaries, and we proved some of them. Following that, we talked about conditional probability, we talked about the total probability theorem, and we talked about Bayes' rule and how we apply them. We talked about applications of these things into wireless communications, digital transmission, and data storage systems. And we concluded the lecture by talking about how to compute probability using combinatorics and the various counting methods. Okay? Today, we move a step forward and we start talking about random variables. So, a definition, a random variable is a function that assigns a real number to each outcome of the sample space. Of our random experiment. So what does that mean? You perform a random experiment, you have the sample space, the set of all elementary outcomes. A random variable is simply a function. This function can be denoted as x of s that assigns a real number to each outcome of the sample space S that belongs to S. All right? Good. How are random variables characterized? Discrete random variables. They are characterized by the probability mass function, Px of x. Observe the notation. So capital X in the subscript refers to the random variable itself. Small x between brackets refers to a value that the random variable takes. Okay? You can definitely skip the capital X, but it becomes a little confusing when you have multiple random variables and you're talking about joint probability, so it's always better to put it here. It also could become confusing if the random variable takes k. Then you're just saying P of k. Okay, k. What is the variable taking k? Okay? So the probability mass function immediately gives the probability. How about continuous random variables? They are characterized by the probability density function, fx of x, that gives the density. All right. This is also, once again, another generic concept that applies to probability as much as it applies to lots of other things. For example, you can have the power spectral density. And here, the probability density. How to get the actual value from a density? Exactly, thank you. So you integrate to get the probability, which is the same thing you do with the power spectral density that you are going to be experiencing with Chagatai Hoja in the third module of the course. And then there is the cumulative distribution function, or the CDF capital Fx of x, which is the probability that x less than or equal to x. It is here discussed in a separate item because it applies to discrete and continuous random variables, albeit it is more used for continuous random variables. All right, expectation, moments, and variance. So we will put the equations for discrete random variables. The expected value of a random variable x is summation over the values it takes, x, px of x. The expected value of x to the n is summation over x, x to the n, px of x. As a matter of fact, you can even replace this by any g of x, and it will be the same. We will see that in functions of random variables, but the logic is the same. How about the variance? V of x is the expected value. This is also referred to as mx, the expected value of x minus mx over all squared, which is the expected value of x squared minus mx squared, that is sigma x squared. Okay, let's look at these quantities and try to understand what is the use of them. First of all, let's talk about the expectation. Can the expectation of a random variable be a value the random variable does not take? Yes? No? Can the expectation of a random variable be a value that the random variable does not take? Yes. So please raise your hand when you talk. Who said yes? Okay. Why? For any of you? Or give me an example. Forget about why. Exactly. If you toss a coin, then you have the head. You can refer to the head with a random variable 0, the tail with a random variable 1. The expectation is a half. Obviously, the random variable does not take the value of a half. Having said that, what is the expected value of a constant? Its value itself, absolutely, which tells you that the expectation does not really characterize randomness. Okay? It just tells you the expected value of your random variable, but does not refer to whether the quantity is random or not. How about the variance of a constant? Zero, absolutely. The variance of a constant is 0. The variance of A is 0. A is constant. And thus the variance is actually the quantity that tells you more about the randomness in your random variable. Okay? When the variance is big, the randomness is high. When the variance is small and it is centralized around the expected value, the randomness is minimal. All right. As for continuous random variables, we will not really talk about them in detail here, but you just replace these summations with integration, so it's nothing like fancy. And replace px of x with fx of x, small f. All right. Discrete RVs, again, and important distributions. First, we have the Bernoulli distribution, where px of 0 equals 1 minus p, px of 1 equals p. The expected value of the random variable is p. The variance of the random variable is p, 1 minus p. And then next, the binomial distribution. Where px of k is n choose k, p to the k, 1 minus p to the n minus k, and k takes a value between 0 and n. Question for you. What is the relation between the binomial random variable and the Bernoulli random variable? Exactly. Exactly. Thank you. So the binomial distribution, the binomial random variable, is essentially a summation of independent Bernoullis. Okay? So the binomial random variable is a summation of independent Bernoulli random variables. So fundamentally, what is this random variable referring to? It is referring to how many successes you have, the number of successes you have out of n trials. You are performing an experiment, you succeed with certain probability, you fail with certain probability. The binomial random variable refers to how many successes, the number of successes out of n trials. Okay, under that logic, we can immediately think about the expectation and relate it to the expectation here. What is the expectation of the binomial random variable? If this one is P, and this one is N out of this one, and they are independent, so what is the expectation? Thank you, exactly. The expectation is N times P, and the variance, just because they are independent, is NP, 1 minus P, and we will talk about it in detail today. How about the geometric random variable? Px of k, P, 1 minus P to the k minus 1. K takes a value between 1 and infinity. There are two variants of the geometric random variable. One variant of the geometric random variable tells that the probability mass function is written this way because the variable is representing the total number of trials until first success. There is another version of it which tells that the random variable refers to the total number of failures until first success. I don't know why this philosophical difference appears, but we will stick to this one. Okay. The expected value of the random variable here is 1 over p, and the variance of the random variable is 1 minus p over p squared. Okay, let's do the first example of today's lecture. Prove that for a geometric random variable, the expected value is 1 over p. Geometric random variable x with parameter p. All right, how to calculate the expectation? The expected value of x is, as we just said, summation over x, px of x, which is summation here over k, px of k, which is summation over k, p1 minus p to the k minus 1, and here k from 1 to infinity. We can just like take 1p outside, becomes summation from k equals 1 to infinity, k 1 minus p to the k minus 1. Okay. Any ideas how can we deal with this summation? Okay, forget about the k. How can we deal with the summation 1 minus p to the k only? If you don't have this k, what is this summation? And this is not even k minus 1, it's just k. What is this summation?
1 over 1 minus p.
Thank you. Summation of a geometric series, infinite geometric series, it's 1 over 1 minus r. R here is 1 minus p. It becomes 1 over p. Correct. But we still have this k. What is this? Okay. What is the relation between these two? What's the relation between this and this?
Derivative.
Exactly. With a minus sign. But yeah, it is the derivative, right? This is the derivative of this. And thus, the expected value of x is minus p summation from k equals 1 to infinity d by dp 1 minus p to the k. Here we can actually replace the summation and the derivative sign. 1 minus p to the k equals 1 minus p d by dp 1 over p equals minus p times minus 1 over p squared equals 1 over p. All right? Everybody's fine? Great. Okay, let's look at the Poisson random variable, and we will spend some time also discussing the Poisson, since later on with Irifojam you are going to be looking at the Poisson process itself. Px of k is lambda to the k over factorial k e to the minus lambda with k equals 0, 1, dot, 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 up to infinity, lambda greater than 0. The expected value of this random variable is lambda. The variance of this random variable is also lambda. Okay. We will try to establish relations between the Poisson random variable and two other random variables. One of them is a discrete random variable. The other one is a continuous random variable. And those two random variables being Poisson to binomial and Poisson to geometric. Now we will discuss the relation between the Poisson random variable and the binomial random variable through an example. Example 2. Let P equals lambda over n. Prove that a binomial random variable with P is approximately a Poisson random variable for large n. What is the way to go about this? Is just we will try to substitute in the PMF of the binomial random variable with this relation given, P equals lambda over n, and see where we go, okay? So, Px of k for this binomial random variable is factorial n over factorial k factorial n minus k times this P will be lambda over n to the k, 1 minus lambda over n minus k. That's for the binomial. All right. The second thing we would like to do is to just like look at this PMF, and see how many terms we have and try to collect the remaining terms, right? We have lambda to the power of k. This is here, but we don't have the other two terms. What can we do? We need factorial k, we need e to the minus lambda. How can we get factorial k? How can we get e to the minus lambda? Summation? Oh, you want to perform an expansion, like an expansion for this and try, okay, that is correct. So let's write it rigorously. Limit as n goes to infinity, 1 plus a over n to the n. What is this? As our colleague here said, when you perform the Taylor expansion, this will look like what? This is e to the a, right? This is e to the a, right? So, when we look here, we can see that as n tends to infinity, as n becomes quite large, n minus k becomes n. And this thing becomes 1 minus lambda over n to the power of n for n large. So this already will give you the e to the minus lambda, right? Now we still have the factorial k. The factorial k is apparently in our equation, but there are some other factorials. When we try to expand these other factorials, we will get to where we want. So the px of k can be written now as lambda to the k over factorial k. And then we have factorial n over factorial n minus k, which is n, n minus 1, n minus 2, dot, 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 n minus k plus 1, divided by n to the k e to the minus lambda. What will happen to all of these terms when n is very large with respect to k? What's going to happen to this term approximately? N, right? This one, exactly. So all of them will end up being also n minus n to the k approximately, and thus we get lambda to the k over factorial k e to the minus lambda, and k 0, 1, 2, dot, dot, dot. It was up to n, now it's up to infinity. Okay. This tells us something more advanced than the math, which is essentially that when you have a binomial random variable, you are trying to pick k out of n objects. When n becomes very, very large and the probability of success becomes very small, then you end up having a random variable with less parameters and n goes to infinity. The binomial random variable, as we have already seen, it has three parameters. It has n, k, and p, right? So it is defined by n, p, and k is the value of the random variable. The Poisson random variable doesn't have all of these. The Poisson random variable other than k only have the parameter lambda, all right? Okay. Done all this. Do you have any questions until now? All right. Continuous random variables. We also discuss directly important distributions. The uniform distribution. Here, fx of x is 1 over b minus a for a less than or equal to x less than or equal to b. What is the expectation of a uniform random variable? Yeah, the midpoint, right? It's a plus b over 2. And the variance of a uniform random variable is b minus a squared over 12. The exponential random variable. Here we have fx of x is lambda e to the minus lambda x. For x greater than or equal to 0, lambda greater than 0. The expectation of the exponential random variable is lambda. The variance is lambda, my bad, 1 over lambda and 1 over lambda squared. And here comes the relation between the exponential random variable and the Poisson random variable, and we will discuss it through an example. If time between events is exponentially distributed with lambda, number of events per unit time is Poisson with 1 over lambda. Okay. All right. What does that mean? Let's assume that you are going to the bank, you and some of your friends, you are going to the bank, and you are just like making some money transfer and leaving, okay? So if the time between events, and the event here can be defined as one of you finishing and leaving, and then the next one finishing and leaving, and then the next one finishing and leaving, and so on and so forth, is exponentially distributed with lambda. So there is an exponential distribution for the time between different events. So when x is quite small, the likelihood is very high. when it becomes bigger, the likelihood becomes smaller. Okay? You could also think about that as if you are doing it alone and going through a bank, that you will have the expected time to finish your thing around here. And it is very, very unlikely in the end to finish very, very late and leave. Well, sometimes it can happen if it is a public bank, but okay. And this tells when you decide some unit time, let's say this unit time, the total number of events, how many of your friends will be finishing their thing and leaving, the total number of events will be Poisson distributed with 1 over lambda. This is the relation between a continuous random variable representing time and the discrete random variable representing number of events. All right? Clear? All right. The Gaussian random variable. Fx of x is 1 over square root 2 pi sigma e to the minus x minus mx squared over 2 sigma x squared, x between minus infinity and infinity. The expected value of x is mx. The variance of x is sigma x squared. All right. Question for you. This random variable is also called the normal random variable. Why is that? Why is this random variable called the normal random variable? What is normal about it?
Expectations
MX. It's MX is, we name it MX, right? There's nothing special, right? What is normal about it? What is normal about it in real life?
We come across with it too much.
What?
We come across with it.
Absolutely. A lot of natural phenomena that the human being does not try to control, does not try to intervene in, will end up being, if random, distributed through a normal random variable. Let's talk about an example that you are quite familiar with. The private universities versus the public universities in Turkey. In the private universities, there is a clear intervention in how things work, right? You pick some excellent students, some pretty mediocre students, and then, yeah, there is a clear difference between the two. So you can teach a course in a private university and the distribution of the grades ends up being highly bimodal. There are lots of good people or a decent number of good people and lots of not so good people. And then the people in the middle are kind of distributed. But this is not the case here. You get to this place only because you are good, not because your family is rich. So when we put your grades eventually, it typically looks like this. Those who like the course and who are really good at the course, they end up being here. And those who didn't like the course or didn't study hard, they end up being here. But because most of students are already good enough, they will pass the course. They will be around here. So all these phenomena that the human being does not try to intervene in, or most of them, they end up having some normal or Gaussian distribution. That's why it's called normal. All right? Good. Let me ask you a question about the exponential random variable just quickly before returning to the Gaussian. Something about calculus. How can you get the expectation of this random variable? It's integration over x fx of x times this thing, and then how you solve it? Yeah, integration by parts, right? Exactly. You will do it through integration by parts. This one, as far as the expectation goes and as far as various integrals go, it will be quite difficult because you will have x squared minus 2x plus something, and then you will have the exponent, and then you will have x here. which becomes quite tricky. But the way to go about some of these integrals, not all of them, we will talk about calculating the probability, but the way to go about some of these integrals is to convert from the Cartesian coordinates into the polar coordinates, where x is r cosine theta, y is r sine theta, and dx dy is r dr d theta. Okay. This is also sometimes referred to as nm at sigma x squared, and the standard Gaussian is referred to as n also 0, 1. So mean 0 and variance 1. All right. How to calculate the probability from a Gaussian random variable? Computing probability. As we said, integrating this guy is very tricky. Sometimes the conversion to polar coordinates will help you, other times it will not help you. So let's try to calculate the probability px less than or equal to small x. How can we calculate this probability? Recall, you probably have passed through this. Through the table, right. Okay, let's try to go through this, dig deep into this to understand what this table is and how these probabilities are actually calculated. All right. There is a famous function called the Q function. Q of x is 1 over square root 2 pi, the integration from x to infinity e to the minus t squared over 2 dt. All right. These tables our friend here was talking about are actually for the Q function. They are not really for probabilities. There is a step we need to make such that we get from our probability into the tables of the Q function. What is this step? What can we do to go from here to here? First of all, what is the relation between this thing? If you forget about the integration sign, what is the relation between 1 over square root 2 pi e to the minus t squared over 2 e to the minus x squared over 2 and the standard Gaussian? What happens when you put here mx 0 and sigma 1? You immediately get this thing, right? Good. So Q of x actually gives you probabilities of the standard Gaussian, assuming that the probability you're seeking is the probability, this is t, and this is fxs of t, assuming that this probability goes from point x forward. Okay, so we are starting to put the pieces into the puzzle together. What is the relation between Q of x and fxs of x? What is the relation between the Q function integral we did here and the CDF of the standard Gaussian? Thank you, exactly. So the summation of the two is, right? One goes from minus infinity to x, and one goes from x to infinity. All right? We are still completing the pieces. Still, we have just one small missing piece, that this thing is not a standard Gaussian yet, because we said this is a generic Gaussian with mx and sigma x squared. How can we make use of these two relations in calculating the probability of this non-standard Gaussian? Convert it to a standard Gaussian, right? How can we convert it to a standard Gaussian? As our friend here said, this is an inequality. We can just do this. Which is the probability that the standard Gaussian Sx is less than or equal to x minus mx over sigma x, which is f xs of x minus mx over sigma x, which is 1 minus the q function of x minus mx over sigma x. Everybody's okay? All right, let's do some additional relations and then we finish the lecture with an example. What is the expected value of ax plus b? What is the variance of ax plus b? What is the expected value of the summation over ixi? What is the variance of the summation over ixi? Let's do the expectations first. What is the expected value of ax plus b? Exactly. So this is a times the expected value of x plus b. What is the expected value of the summation? Sum of the expectations. Okay. Okay. This is very, very, very important. It's not even easy to emphasize on how important this is. Does it matter whether they are dependent or independent? It doesn't matter. Dependent, independent, it doesn't matter. The expected value of a sum of random variables is the sum of the expectation of the random variables. Their dependence, their correlation does not matter at all. Right? This is very important. It opens door to solving lots of problems without the need to do hectic mathematical calculations, and we will see this today. Okay, what is the variance of ax plus b? It is a squared v, because the variance of a constant is 0, right? What is the variance of a sum of random variables? Okay, when does the variance of the sum of random variable becomes the sum of variances? Yeah, that's the stricter condition, but when they are uncorrelated, it suffices. But yes, if they are independent, they are uncorrelated, not the other way around. So you could think of this as it is the summation of variances plus something, and that something is the summation of covariances for all I and j, covariance xi and xj. What are, so we already said that independence, bless you, independence, uncorrelated does not imply independent. Independent implies uncorrelated. What is the only group of random variables where if they are uncorrelated, they are also independent? There is one group of random variables that, if they are uncorrelated, they are also independent. the jointly Gaussians. Okay? So random variables that are individually Gaussians and jointly Gaussians, if they are uncorrelated, they are also independent. Okay? But this is not a common case. Why is that? Before we move on, because this is the condition of independence. And this is the condition of the variables being uncorrelated. Which condition of the two is stricter? Which condition of the two leads to the other? What is more strict, if the entire distribution is the same or if only the expectation is the same? The entire distribution is stricter, right? So this one leads to this one, but not the other way around unless they are jointly Gaussian. Okay? So we will do one last example. So all of you have the lecture in front of you, one way or another? Okay, so I don't really need to write the example in detail. The last example we'll give today is example 3. M football games. M distinct tickets. Choose from a pool of infinitely many folded, unfolded tickets. And each ticket is equally likely to be for any game. Find the expected number of tickets to unfold. How many of you like football in any way? Okay. Small number though. You are in Turkey, not in the US. Okay. I didn't say American football. Okay. So let's assume that there are M football games, and for each game you have a distinct ticket. You want to attend all the games, and in order to do that, you need the M distinct tickets. You choose from a pool of infinitely many folded tickets, and the odds that a ticket refers to any of the game is the same. Okay? Find the expected number of tickets you need to unfold in order to be able to perform this task. Okay. This is an example where this relation is a life savior. And in addition to that, it's an example on the idea that you do not need to get to the underlying distribution to find the expectation. This is very important. Some random variables are too advanced to find their distribution, and then after you find the distribution, you do summation over x, x, px of x, or integration. It will not work in many, many situations, and that is one of them. Sometimes it will work, but it will cost you a lot of needless calculations. Others, it will be way too complicated. Okay, we will start first by decomposing this event into a series of events and try to think about them. So the event of getting ticket to first game, or let's say first new game. I don't want to confuse you. I don't here mean game 1 in particular. I mean the first new game, a game you do not have. And then getting ticket to second new game. And then moving on until getting ticket to nth new game. Let's try to calculate the probability, which is essentially conditioned on what you have. So in the first scenario, you are trying to get a ticket. What is the probability that the ticket you will get will give you a new game? The first new game, 1. Exactly. You get anything is a new game. You have absolutely nothing, right? How about the second one? Exactly, thank you. M minus 1 over M. The same logic for the third, M minus 2 over M. And then the last one, which will be the most complicated one, like you got all of them and you keep drawing until you get the mth one. So obviously this one will cost you some time. Okay, let's use this magical relation right there, the expected value of the summation from I equals 1 to M T. This is the expectation we are seeking, the expectation of the compound event. Let's call it E all is E, which is the expected value of the summation. This is the summation from I equals 1, the expected value of Ti equals the expected value of T1, expected value of T2, ... plus expected value of Tm. All right, we have some probabilities for some individual events, but we still don't have expectations. We want the expected number of tickets to unfold, not the probability. Look at any variable, or look at any event of this. Look at this event. And think about it in terms of the random variable representing that event. Is that random variable anything we have looked at today? Keep drawing until you get the ticket you need. What's up? Geometric, right? So each one of them is an individual geometric. So what is the expectation? Say geometric for xi. And the expectation in this case is going to be 1 over its p, which is m over m minus I minus 1. All right, so this thing is going to be m over m plus m over m minus 1 plus ... plus m, which is m summation from I equals 1 to m 1 over I, which is m something. What is this? You have definitely seen it in the past, one way or another. Okay, it is called the mth harmonic number. Have you ever heard about this term before? It's called the harmonic number. You have heard about it like somewhere. You know when the instructor writes something at the end of the board and leaves, it's something like that. So it's something like that, yeah. And this thing is approximately ln m plus something of order 1, which is m ln m plus something of order m. You aware of the big O notation? Okay, you have a binomial. If you have a binomial expression, the big O notation would refer to the dominant term. Okay, the dominant term. One last thing, and then a quick note about the homework. Can someone think about something intuitive that can lead us from here to here without the mth harmonic number? Just like something intuitive that can get us from here to here? Just by intuition, what is the relation between this like 1 over something and ln something? Absolutely, thank you. Yeah, right? So if you think about it as an approximation and as if this is an integral, this would lead to this immediately, right? But since it is a summation, not an integration, you have an extra residual term out there. Okay, that's all for today. So probably we will be posting the first homework either in the weekend or early next week. And until now, the idea is that you will be submitting it on Sunday night, the following Sunday night. So if you have any question about the lectures or anything, you can pass by my room, you can send an email, and see you next week.